Hi guys, today I'm going to talk about program synthesis and what happened when we give it to users. So before I begin, I would like to note that there are a lot of techniques for program synthesis, and in this talk, whenever I'm going to refer program synthesis, I'm actually going to mean programming by example. In this technique, the user provides the synthesizer with a set of input-output examples, and the synthesizer will then try to find a program that satisfies all of them. One example of such tool is Loopy. It is a work from a few years ago that integrates a synthesizer into an IDE with live coding features. And as you can see here in the screenshot, this gray box near the code is called a projection box, and it actually shows the user the live values that each variable gets at this line, meaning that the IDE is continuously evaluating the code and showing the user throughout those projection boxes the live value that each variable gets. Later on, when the user would like to generate some code, he can invoke the synthesizer by typing $! Loopy will then use the projection box as an interface for the user to provide the examples. It will take the live values as input for the examples, leaving the user to only provide the output. And here you can see how the user can specify one example. But if the user would like to specify the code using more than one example, he can just add another call to the function. The projection box will be re-evaluated, and the user can now specify using more than one example. Okay, so this is Loopy, and this is how it basically works. And now I want to show you a full synthesis session and what it looks like. And for that, I'm actually going to need a task. And the task that is going to follow us today is the run length encoding compression task. This is a task from cracking the code interview. And as its name applies, the task is to implement a string compress function, and the compression should work like this. So imagine we have this input. We would like to replace the sequence of A with 2A, B would be replaced with 1B, and the sequence of C should be compressed into 3C. So this is the basic task. But before trying to solve this, let's focus on the heart of the task, which is going to be the concatenation. So let's try to synthesize a function that gets a character and a number and concast them together. So how it should look like. The user will invoke the synthesizer and get this projection box to fill. And let's say that in the first iteration, the user will only provide one example. So he will fill the first row, press enter to send the example to the synthesizer, and the synthesizer is going to return this program. So as you can see, on the one hand, this program does satisfy the example, but it's not the general case program the user was hoping to get. So at this point, the user understands that he needs to specify using more than one example. So we'll try again. He will delete this line, invoke the synthesizer, and it will get the same projection box to fill. And this time, he will try to give two examples. So he will start by filling the first row, and by accident, he will make a typo. So instead of 2A, he put 3A's, but he didn't notice and continued filling the second row. He filled the second row, pressed enter to send those examples to the synthesizer, and got this piece of code. Now the user is a bit confused. I mean, after sending the example to the synthesizer, the examples are no longer visible to him, so he can't really tell that he made a typo. And when he looks at the code, he sees this constant tree in the code, but he can't really recall that any of his examples contain the tree. So he's like, what's going on here? At this point, the user is, like I said, very confused and probably thinks to himself, okay, I'm going to give this tool another one try, or I'm going to move to ChatGPT. So he will invoke the synthesizer again, and like before, he will get an empty projection to fill. So he will need to fill the first row again, the second row again, and adding a new third example, he will fill the third row, sending those examples to the synthesizer, and finally get the program that he actually wanted. As you can see, this process of reproviding the same example that you already provided is a very tedious and error-prone process. But this is not all. I mean, what happened next? After the user got the program that he was satisfied with, he will take this piece of code and compose it together with the code that he wrote by himself, leaving no evidence that actually this line of code was synthesized and should be looked at with extra care. So to solve those problems, we propose example scopes. Basically, every solution that the synthesizer is going to provide us, we will wrap with those comments. Since the solution can contain more than one line, we actually need to mark where it starts and where it ends, and this is what gives us the scope structure that we are actually wrapping something. So as we said, we mark where it starts and where it ends, and we're also going to keep the example that the user provided in the comments themselves. And the structure of the structure of the example is quite intuitive, where the inputs are on the left and the outputs are on the right. Now I want to notice that those comments are just a normal Python comments, meaning that the user can modify them. He can delete them, edit them, and more importantly, he can also add more of them. And of course, the user can also modify the code inside of the example scopes. Therefore, we decided to add some live feedback to those comments, meaning that we are going to evaluate the comments over the code and show the user if the code that those comments wrap actually satisfy them or not. So here you can see that all of the examples are satisfied, but if the user will modify the second example, the code doesn't longer satisfy it, so we will color it in red, telling the user that it's not satisfied. At this point, and like in every other time of the program, the user can invoke the synthesizer on those example scopes, and what it's going to do is that the synthesizer is going to parse those comments, it's going to take those examples, and we'll try to find a program that satisfies those examples. So this is basically the beginning of a tool that we call ScooPy. We start by keeping those example scopes in the code, and also add some live feedback to those comments. So we can say that by allowing the user to invoke the synthesizer on those example scopes, we change the interaction model, eliminating the part where the user needs to retype the same examples all over again. Okay, so after we have the example scopes, let's go back to the original task and try to see what this extra ability that we provided user can cause. So here you can see a scratch of the solution for the compressed task, where we are iterating over a string, and each iteration we are going to check if the current character that we see is equal to the last character that we saw. If so, we are going to increment a counter that counts how many times we see the same letter. And let's say that we want to synthesize the else part of this, the else part of this code. So imagine we are at this state of the program, that we see B after we saw A twice. The state is what you can see on the left, and we want that after the code in the else branch would be executed, the state to change to something like this. We would like the rs variable to contain the concatenation like we see before, so to A. We would like to update the last variable, so it should be B. And we also want to reinitialize count to 1. So if we take this example and give it to the synthesizer, we will get this piece of code. And as you can see, like before, we have this overfitted assignment to rs. The concatenation is overfitted. At this point, we will actually try to synthesize only this assignment. So we'll delete this line, and we'll provide the synthesizer now with 2 examples to get a piece of code that seems to do the job. And it seems good. I mean, we fixed the code, but what happens if we take a broader look at our code? I mean, the first example that we provided is now colored in red, meaning that the code it wraps doesn't longer satisfy. And why is it? I mean, we fixed an overfitted code, but we actually discovered a bug. If you look closely, you can see that we actually reinitialize count before actually using it. So each time the result is going to be like 1 something, which is obviously not satisfied the example. And another thing I want you to notice is that by allowing the user to synthesize inside of an existing example scope, we actually created nesting of those scopes. So here you can see the inner example scope that is wrapped with an outer example scope. So nesting occurred. At this point, the user would likely to invoke the synthesizer on the outer example scope, hoping to get a program that satisfies this example. And what is actually going to happen is, like we said before, the synthesizer is going to parse the example in the example scopes, ignoring everything inside of it. It will take this example and will return us this piece of code, which is actually the same code that we started with the overfitted assignment. So this is not quite a good idea. At this point, we had 2 options. One option is going to limit the user and not allowing it to synthesize inside of an existing example scope, so no nested could be created and no problems. And another option was to improve the synthesizer and make it take into account those nestings. So as you may guess, this is the reason I'm standing here. We chose the second option. And like I said before, we start by keeping the example scopes in the code and add some live feedback to them. But we also propose a new synthesis algorithm that takes into account nested examples. So before I'm going to show you how it works, let's go back to the code. And just for the fun, and so I could explain more in detail later on, let's wrap the entire body of the loop with another example. So here you can see we added another example that wraps the if-else. And if you notice, we have now nesting in depth 3. We have the innermost example scope, the middle scope, and the outermost example scope that wraps all of them. So before explaining what is going to happen, I want to show you a small demo of the tool. Great. So here you can see the state that we left the slides. We have the innermost scope, the middle scope, and the outer scope. And the first thing I want to show you is that if we hover over the example, actually the tool is going to say why this example is not satisfied. It tells that RS is expected to be 2A, like it's written here, but after evaluating the code, the result is going to be 1A. I also want to show you that if we will modify the examples, it will also reevaluate and color it, and this is also true if we will modify the code itself. Plus. So the examples are now red. And the most interesting thing I want to show you is what's going to happen if we invoke the synthesizer here on the outermost example scope. So let's say the user will invoke it. The synthesizer will think for a bit and will return us this program where all of the examples exist actually and satisfied. And if you noticed, we actually took the example that wrapped the entire else branch and brought it up to this. I'll explain later on why this actually happens, but basically we got code that fixed the order of assignments, so we are happy. So that's for the demo. Let's go back to the slides and explain what happened. So, like almost every good thing in PL, it all starts with the AST of the program. So you can see here the AST of the program that we had. And since we added the example scope to the code, we also need to represent those example scopes in the AST. And we do this by showing those green boxes. So each box wraps the code that corresponds with the code that is wrapped with the example scope. And when invoking ScooPy and those example scopes, it will start to iterate over this AST and try to find a program that satisfies those example scopes, and that the iteration of actually synthesize will take into account the example scope's location and their relation with one another. So the iteration is going to be a bottom-up iteration, meaning that we are going to start from the innermost example scope. And the algorithm goes like this, that and each time we're encountering an example scope, we actually need to look at the node's parent. So if we do this, we can see that E2 is a part of sequence of assignments. And at this point, at this case, we're actually going to take a flat synthesizer. I mean, a synthesizer that can find a program that discards with only normal examples. We'll take the examples from the example scope, send them to the synthesizer, and get a program that satisfies those examples. We will keep this program aside, knowing that we need to include it later on in the solution, and continue the traversal. So we continue, and we can see we're encountering another example scope, E1. Like I said before, we need to look at the node's parents, and we can see that E1 is a son of an if-else node that is also wrapped with an example scope. In this case, we're not going to take E1 and send them to the synthesizer. We're actually going to do something more sophisticated. As you can see, E1 and E3 actually describe the same code block, you can think of it. So we actually can unite them. So we will do this before sending them. So we will unite the examples. But the union is not a normal union. We also want to remember that the example from E1 came from the same branch of the code. I mean that later on, if we have also an if-else in the solution, we would like to keep the example from E1 describing the same branch. So after the union, we will take the code that you found earlier, send this to the synthesizer, and ask the synthesizer to find a program that satisfies this example union, but also include the program that we found earlier. So the synthesizer is going to return us something like this, a program that satisfies E1 and E3, but also include the program that we have before. So this algorithm that I just showed you with the animation can be described with those inference rules. So for example, the cond rule tells us what to do whenever we encounter an if-else node. And those two scopable rules describes as what I described as looking at the node parents and decide what to do based on it. And any question of those inference rules? I guess no. So let's do a small recap of what we saw. We started by leaving example scopes in the code. We added them some light feedback. We saw that those example scopes could be nested one in each other, and we also see how we took a synthesizer and make it find a program that satisfies all the examples. Okay. At this point, we want to see if this new ability that we gave the synthesizer actually affected the expressiveness of it, meaning that is the synthesizer is now able to find a program using less examples. So to do this, we started by collecting 50 programming tasks and started specifying each of them using nested set of examples. Later on, we took each task and we also need to describe them using only top-level examples. So we took each nested examples and removed the nested examples, leaving us with only top-level examples for the program. And we gave those top-level examples to the synthesizer and saw if the synthesizer was able to find a solution. If it didn't able to find a solution, we added more examples, tried again, so on and so on, adding more examples until the synthesizer was able to find a solution, or we needed to add 5 examples and then we stopped because we didn't want to add more than 5 examples. So at this state, you can imagine we have 50 programming tasks that are described once with nested examples and once with top-level examples. And we wanted to calculate the difference in the total number of examples for each description. So imagine we have this scenario where a task was described in the nested form using 4 examples and in the flat form using 3 examples. We say that the difference is -1. But if we have a program that is described with 4 examples in the nested scope, in the nested form, and with 5 examples in the flat form, we say that the difference is positive. So as you can see, the difference can also be negative and also can be positive. And of course, it can also be 0. So here we show you the number of benchmarks that the flat synthesizer was able to solve as a function of the difference that we just calculated. So like we said, we have 50 benchmarks that ScooPy was able to solve. Out of those, 40 benchmarks the flat synthesizer was able to solve, and the remaining 10 the flat failed due to a timeout or that 5 examples weren't enough, and then we actually stopped. In the negative part of the graph, you can see the benchmark that the flat synthesizer was able to solve using less examples. And in the positive part of the graph, you can see the benchmark that he was able to solve, but he required more examples. So if we sum the number up, we can see that ScooPy was able to solve more than half of the benchmarks using less examples. So we actually gained some expressiveness. So yay. After that, we wanted to check ScooPy's ability with real users. So we conducted 2 user studies. One user study was in order to test the effectiveness of example scopes and the live feedback we gave them, and another user study to test the ability to synthesize nested example scopes. So let's go to the first user study. The first user study was within subject study that had 6 participants, and the research question that we wanted to answer was, does keeping specification help understanding synthesized code? And in order to test this, we actually created 4 debugging tasks by synthesizing each line of the task. And you can see on the left the control settings, where we did not include the example scopes. And on the right, you can see the same code, but actually with example scopes. And we asked participants to find the bug and fix it. here you can see the time it took each participant to solve each task, where the dashed line represents the average time it took for each group. And as you can see, in all of the tasks, participants who had those example scopes actually took more time to solve the task. We believe this is because they were more engaged with the examples and the code itself. One of them told us, I don't think there is any problem here, but let me just add another example, meaning they were like playing with the examples. Another thing I want to note is that each participant who started solving the task with example scopes asked them back when he moved to task without them. So it's nice to know. Moving on to the second user study, it was a between subject study that we split the participants into two groups. One group got ScooPy, which is its full ability to synthesize nested example scopes, and the other group got ScooPy, but when trying to invoke the synthesizer on nested example scope, the synthesizer is actually used only the top level examples, ignoring everything else, like we saw before. And I'll just say that both groups went to a guided first task, knowing the ability of the tool, meaning the first group knew that the synthesizer is going to take into account nested scopes, and the other group knew that the synthesizer is not going to take them into account. And the research question that we wanted to answer was, does the ability to synthesize nested example scopes help programmers? And help programmers in two scenarios. One, does it helpful with unfamiliar code? And another, is it helpful with a familiar code? And actually, to create a familiar code, we needed to add another middle task, a scaffolding task, where we ask participants to synthesize code, so we have some code that they are familiar with. So let's go to the first task, the unfamiliar task. So like before, we measure the time it took each participant to solve the task, and those are the bars you can see here. The dashed line represent the average time it took each group, and bars with hatches represent participants who did not finish the task due to a timer. So, like you can see, the success rate of participants who had the ability to synthesize nested example scopes was higher, and the time it took them to solve the task was lower. So it's a good thing. And if we move to the scaffolding task, we actually did not expect to see any difference in the result because there was no need to resynthesize nested example scopes. And like we expected, we actually didn't see any time difference. Moving on to the familiar code task, this time we saw that participants who had the ability actually took more time to solve the task. And we believe this is because the participants were more afraid to invoke the synthesizer on those nested example scopes, because they were not sure actually what is going on behind the scene, in comparison to the other participants who actually knew exactly what is going to happen. And they told us this throughout the whole study. I mean, one of them told us that if I touch the outer scope, it will disrupt all the inner, and if I synthesize the outer scope, it would delete everything. I mean, it's not that they were happy with this, but they actually know that the synthesizer is only going to use the outer scopes. We also saw this in a survey that we conducted after the study. One of the questions that we asked them was, did you trust synthesized code when resynthesizing multiple nested examples? And also here, we can see that participants who actually had the ability to synthesize nested example scope trusted the code less. So to sum up, we saw ScooPy. It starts by keeping example scopes in the code, add some light feedback to them, and propose a new synthesis algorithm that synthesizes nested example scopes. Or in other words, enhancing program synthesis with nested example specifications. Thank you.
So I have time for a few questions. Please go ahead.
Nice talk. I was really curious about the conclusion of having the comments, because with prompts, they're deciding on doing exactly the same thing, having the prompt as a comment in the code. My question was actually about when you synthesize the top level and you provide the current synthesis for the lower nested example as an ingredient. you don't the synthesizer doesn't modify that ingredient at all, right?
Yeah.
But it could be the case that you have a overfitted example, and for instance you have a constant 2 or whatever, that when you synthesize the outer block, you might want to replace it with a variable that's available outside. That would make the inner code examples work, but make the function more general. Would it be possible to modify the synthesizer to include it?
Yeah, actually, I think so. I mean, the requirement to include the same code as is could also be modified. So I guess if you have some innovative ideas to actually make it use other pieces of code that we can see or new pieces of code, it's all possible.
Okay, thank you.
Thank you very much for your talk, and I think it's a very nice idea to build an explicit relationship between the examples and the synthesis code. But I'm wondering, when the set of input-output examples is becoming really large, would it be difficult to manage or understand the synthesis code even with ScooPy?
If I understand what you ask, I mean, like, if we have like big example, I mean, a lot of in the input state and a lot of in the output state.
Oh yeah, a lot of examples.
A lot of examples or
Yeah.
large examples?
Yeah.
A lot of examples?
Yeah.
I mean, I think it's going to be difficult to understand if you have actually a lot of examples, but the good thing is if we have a synthesizer that is able to solve more general code using less examples, this actually is going to be great. I mean, if you can specify the same code using less examples like we show here, I think you would need like less examples, so you don't have this example.
Okay, thank you.
Thanks for the talk, really cool stuff. Just a very tiny technical question. So if the user would refactor, for example, rename one of the variables, will that be also propagated to the comments, or? Yeah.
Okay. Yeah. Just to clarify, if you will modify the code or the examples?
Either way.
Basically, ScooPy is only going to look at the examples. I mean, he doesn't look at the code at all, as like if you can see here in the algorithm. You can see that the code is actually absent. I mean, it look only at the examples. So the most important thing is the example that you're actually going to provide. So if you modify the example, the code is going to correspond to that.
Yeah. Thank you.
So are there any further questions? Should thank the speaker then, and that brings us to the end of this session.